Hello, discrete math fans. Let's talk about equivalence classes. Let's suppose we have an equivalence relation on a set A. Remember what that means. It means that the relation is reflexive, symmetric, and transitive. Let's say we take a particular element, little a. We can ask, what is the subset of all elements that are related to little a? That subset is called the equivalence class of A. So we'll make a definition to say that if A is a set and R is an equivalence relation on A, for each element little a, we're going to define the equivalence class of A, and we'll write A inside brackets, and we'll just call it the class of A. It's the set of all elements X such that X is related to A by R. So in symbols, we'll just say that the class of A is the set of all things in A such that X is related to A. All right, so let's take this as an example. Our set A is going to be the set containing 1, 2, 3, 4, 5, 6. We'll define a relation R using a directed graph. All right, so here's our picture that shows our elements in the set, and the arrows indicate the relation. You can see arrows going to and from various elements in the set. And what you should notice is that this is actually an equivalence relation, right? It's reflexive, it's symmetric, it's transitive. And our goal here is we're going to write down the distinct equivalence classes of R. All right, so what we'll do is we'll find the equivalence class of every element in A, and then that'll lead us to find the distinct equivalence classes. So the class that contains 1, that's the set of everything that's related to 1. That's the set containing 1 and 2. The class of 2 is the set of everything that's related to 2, and that's the set containing 1 and 2. So if we run down the line, we can compute the equivalence class of each element in the set. But notice that we get some duplicates in here. So when we want to write down the distinct equivalence classes, we're only going to write down 3 things. See, we can see that the class of 1 is the same as the class of 2. The class of 3, 4, and 5 are all the same. And so the distinct equivalence classes of R are these things: the set containing 1 and 2, the set containing 3, 4, 5, and 6 is by itself, right? If you go back to the directed graph, nothing connected to 6 except 6 was connected to itself. And that's it. Okay, that's all for now.